So, dear students, welcome to another lecture of digital control systems. In this particular lecture, we will understand the concept of reduced order state observer. As we have already discussed that a state observer is basically an algorithm or a technique which is used to estimate the states of a given system because there is a requirement for the state regulatory design and state feedback design that if we want to place all the closed loop poles of the given system on the desired location, so uh, all the states of the given system should be observable. Okay, that means they can be directly measured. And if we want to measure all the states of the system, then uh, all the states of the system should be observable, one thing. And second is that we need that many number of measuring instruments to measure all the states of the system. So this is not an economical idea. Okay, this is because it won't make or keep the system cost effective. Also, it is practically very difficult, and in some cases, it is almost impossible to measure all the states of the system, right? So in this case, we make use of the state observers. So we have a full order state observer which actually can measure all the states of the system. Then we have a reduced order state observer which can measure less than n states of the system, right? So full order state observer can reconstruct the entire state vector. Reconstruction here means that it can estimate all the states of the system, right? Then uh, now there is a possibility that we have the measurements available for some of the states of the given plant, right? What it means that, for example, if we have, let us say, four states of the system, right? If we have four states of the system, there may be possibility that two states or one state can be measured, right? So there is a possibility. So rest two states or three states we need to estimate. Now in full order state observer, we can estimate all the four states. Even if it is measurable, we can estimate it. Okay, so now the measurement of a state will give you more accurate value as compared to its estimated value. Remember one thing. So if you can measure a state, it is better to measure it. Otherwise, if it is very difficult to measure a state or almost impossible, then estimate it. So if you can measure directly or conveniently a state, so that is much better because it would give you more accurate value than the estimated state, right? However, it is not a logical idea. It is not a sensible, consideration that we estimate all the states of the system, even that state also which can be measured, right? So if a state can be measured, let it be like that only. We should estimate only those states which cannot be measured, right? Difficult to measure or impossible to measure, right? So in full order state observer, it can estimate all the states irrespective of the fact that the state is measurable or not, right? However, uh, the reduced order state observer, is beneficial in such conditions cases, right? Uh, now, okay. So, state observer basically, it also acts as a filter to, the noise in the measurement, right? So, we will not usually want to estimate any state that we are measuring. This is very true, very factual thing that if you can measure a state, it's better to measure it, right? Do not estimate, right? Because estimated value is an estimated value. Measured value is a real-time value, right? So it is more accurate than the estimated value, right? So we should design an observer that can only estimate the states which cannot be measured. And such type of observer we call as the reduced order state observer, right? So now let us see what is this. Okay, so a reduced order state observer, if there are, let us say, n states of a system, right? If a system is of nth order, okay, so the reduced order state observer will, for a given system, which is given here with the equation number one, which is this one, okay. So the observer which can estimate fewer than n states of the system is the reduced order state observer, right? So if we have a system, this one, right? So for such system, we have X, which is, nothing but a state vector. U is a control variable. Y is an output variable, right? These are real parameters, okay? So X is n into one state vector, right? Like this. Okay, so now, now because the output is a vector, right? And it has dimensions p. So we may have outputs. We may have one output. We may have many outputs, right? And number of outputs are generally less than the number of states. So we have to design an estimator which can estimate n minus p, state. Means the order of the estimator is n minus p, right? If there is there is two states of a system and there is only one output, then you can say the estimator's order would be first order, right? So now let us come to, so we develop a design equation for such an observer in this particular section, okay. So here we will consider one uh, uh, state which can be measured and one state which we will estimate, okay. So let us assume that this is a system which has 2 by 2 dimensions, right? There are, okay, so one state we will assume to be measured and one as estimated, right? So now, okay, so now let us see. So it is assumed that the state variables are always chosen such that the state measured is x1k. That means the first state we will assume can be measured, and the next state we will assume that it is estimated, right? So the output equation, if only one state is available to us, if only one state x1k is only available, because xk is the state vector which may contain many state, right? So x1k, x2k, and let us say xnk, right? So we may have many number of states. So if we have only one state which is measurable, so in that case, y output will be equal to this, because yk is actually, it is equal to c vector, and then we have x1, x2, and so on, right? So if only this is available, so that means we have uh, uh, yk is equal to x1k. So here c is taken as 1, 0, right? So it is a 2 by 2 system, right? So this is, let us say, equation number 2, this one, right? Okay, so now if we want to derive the reduced order observer, so we will partition the state vector into two parts. So that means we will consider the state vector as two different types of states. One is measurable state, which can be directly measured, which is, let us say, x1. And second is the estimated state, which is, let us say, xe. So the state vector can be written as x1k and xek. Okay, so this is, for example, equation number 3. Now, if we partition the system matrix means F matrix. So system matrix is nothing but the F matrix, and also G matrix can also be considered, right? Though it is an input matrix, right? So we have new kind of representation of the given system. So what did we do? We kept this x1k as it is, right? So in place of f12, f21, and this matrix here, So we have these estimated elements. These are the estimated values actually. And this is the real value. Okay, means the value belongs to the real actual system matrix. Similarly, the control matrix has also been divided or partitioned into two categories. One is the actual element of the control matrix, and the second one is the estimate. This is the estimated, right? Okay, and we have the actual state dynamics, and then we have the estimated state dynamics. So this is the estimated state dynamics, right? Right. So now let us come to, okay, then similarly we have the output equation. Okay, so the output equation is taken from here, right? It is taken as it is, and we have replaced xk with this one. So we have got equation number 4b, right? So now, okay, so we will take out this partitioned equation from here, this xek plus 1. So if we take xe, if we solve this one, so we'll get xek plus 1 is equal to, so just, okay, so it is equal to fe1 x1k plus feexek plus geuk, right? So let us see what is this. So it is that one only. So here this fe1 x1 geuk, these are the known inputs, right? These are the known inputs because if you see here, we have simply replaced F12 because we have the F matrix, system matrix. We kept F11 as it is. We replaced F12 with FE1, F21 with FE1, F1E and E1, right? Like this. So we have this equation. This is the estimated state dynamic. Okay. So this equation describes or signifies the dynamics of the unmeasured states. We have some unmeasured states also here, like this is an unmeasured state, right? Okay, xek, this is an estimated state, right? Okay, so these are the known values which is known to us, right? And now, because in equation 2, the equation 2 was, if you go back to the equation 2, so this is equation 2 here. So in this C matrix is this one. So if we consider this here, right? So we have x1 because it is equal to y. So if we take its dynamics difference equation, so x1 k plus 1 will be equal to y k plus 1, right? So that means we have the measured dynamics here. Measured dynamics means the output dynamics are now involved here, right? So we'll use equation number 4a. So how did this equation come into existence? So if we see the equation number 4a, right? So let us see equation number 4a from this, So if you see equation number 4a, so if you replace this x1k with yk, and if you replace this x1k plus 1 with yk plus 1, so you will get yk plus 1 is equal to f11yk, right? And then we have plus f1e into xek, right? And then you have g1uk, right? Okay, so this part has the unmeasured state. Okay, this part has the unmeasured state. So remember this one, yk plus 1 is equal to f11 yk and this one, right? So this equation has been simplified here. So we have the same equation written here in terms of the unmeasured states, right? So here all these are known to us because this is nothing but this is yk plus 1 is nothing but it is equal to x1k plus 1, right? Okay. So now these two equation number 5 and 6. Okay, so these two equations can be related to equation number 1. The equation number 1 is actually this equation xk plus 1 is equal to fxk plus guk, and yk is equal to cxk, right? Okay, so we can relate this here, and then okay, so now if we replace x in this equation with xe, f with f double e, g uk with this equation here means we are simply trying to relate. Okay, we are trying to relate. Okay, so if we see this xe as x, f double e as f capital F here, and then guk, this whole combination if is replaced with guk, and yk is replaced with this, is replaced with yk here, and c is replaced with, if this one is replaced with f1e. So we will get the same equation, xk plus 1 is equal to fxk plus guk, yk is equal to cxk, right? Okay, so when we compare this equation with these two equations, we'll get these parameters. And now what will we do? We will simply try to replace these parameters which are present in the full order state observer, right? So we will substitute these in full order state observer equation, and then we will simplify that equation. In that, on simplifying that equation wherein we substitute these parameters into the full order state equation, after simplifying that equation we will get a reduced order observer. Now full order observer is this one, which is given by equation number 8 here, right? So here, this is the full order state observer equation, right? So in this, we will replace F with F double E and G with that one. So if we replace all those parameters here, so we'll get this equation. This is equation number 1. So this is the reduced order state observer equation. Here we have these inputs which are known to us. We have these measurements which can be measured, which can be, means these are the values which can be measured. And then we have these unmeasured states here, right? These are the unmeasured state, and this indicates the dynamics of the unmeasured states, right? So now in this, if we, now we have to find out the error equation also, right? So this is similar to the full order state observer. So there we get F minus MC matrix. Here we are getting F double E minus MF1E matrix, right? So this is what we are getting, right? So when we subtract equation 9 from equation 5, so what is equation 5? Let us see. So this is equation 5, this one. So if we subtract these two equations, we'll get a difference equation which indicates, which describes the error behavior of the system. Error behavior, right? So you can see here, this is the error dynamics, this is the error, estimated state, and this is the error dynamics of, or error of the estimated dynamics, right? So, okay. So now, then ultimately we find out the characteristic equation. See, the purpose is to find out, the characteristic equation which can be related to the desired characteristic equation, so that we can find out the values of the elements of unknown matrices. Here in this whole scenario, this is the unknown matrix here, right? And others are the estimated values, right? Okay, so this is the characteristic equation. So if we can find out the value of element matrix M, if we can find out the values of the elements of matrix M such that FEE minus MFE matrix, this can place the required closed loop poles to the desired location. So we have this state observer, reduced order state observer available to us, right? So, okay, so our purpose is to select M. The purpose is to select M so that this equation can match with the desired reduced order characteristic equation. So how will you get a desired reduced order characteristic equation? It is always given, right? So we will compare these two equations, desired reduced order characteristic equation and the characteristic equation given by equation number 11, right? So when we compare these two, we get M, right? So this M matrix is the problem for us, which we have to find out, right? Okay. So now there is one thing which you have to observe. Now here, if you see equation number 9, this one, So in this equation number 9, we have this state dynamics of the unmeasured states, right? Which depends upon the dynamics of the output, right? We have this equation, which is uh, a bit, practically it is very difficult to have this kind of situation, right? Wherein we have the dynamics in the output also. So dynamics in the output means that, uh, if your output is noisy, so your noise will be amplified to many folds. So if noise will amplify, so in that case, it is better not to use yk plus 1 in the equation, in the observer. So we'll try to eliminate this term. Now, how will we eliminate this term, right? So for this, we will assume a new state such that we have a new state xe dash k, which is, let us say, equal to this equation, right? And this is, let us say, equation number 12. Now, the difference equation of this equation number 12 by replacing k with k plus 1. If we replace k with k plus 1, so we will get this equation. Okay. So now we will rearrange this equation number 13 in terms of myk plus 1, right? So when we do so, if we rearrange this equation and we get my, so here m is different. It is a matrix. Yk plus 1 is a vector, dynamic vector of the output, right, of the system. So we have this equation number 14. Now what we will do is we have the, equation number 9. So we have, if you see here in this, if you open up this bracket here, so you'll get myk plus 1. So we will try to replace myk plus 1 here, right? So let us see. So we can rearrange equation number 9 and we can write this equation number 9 in this form also, right? So if you go back to this one, so what we have done, we have simply rearranged or simplified this equation to get equation number 15. So we have got this equation number 15 here, right? So if you see here, we have myk plus 1. So we can replace this with this equation here, right? Okay. So when we replace it, we'll get this one. So if you see here, these two can be cancelled out here, right? So we have this equation and we can rearrange this equation and simplify this one, equation number 16. So when we do so, we get a new equation which does not have the dynamics in the output. So our dynamics in the output now are eliminated, right? So it is better to eliminate dynamics in the response, right? Because it is practically, unacceptable situation, right? It is not accepted at all, right? So now this equation can be represented in a block diagram, which will give us the reduced order observer, which is shown here. So you can see this equation number 17 has been represented with this block diagram. Okay, so this is our reduced order state observer. Equation number 9 also represents the reduced order state observer, but the only problem with equation number 9 is that it has the dynamic output. Okay, means dynamics in the output, right? So we have simply eliminated those dynamics and we have got this equation here, right? Now, okay, so this is it for today's lecture and thank you so much.